In terms of remote sensing, GIS, we have four main types of resolution that we need to talk about. We have spatial resolution, how small something is that can be measured. This, especially in terms of remote sensing, we usually think of something called ground sampling distance. What's the area on ground that is equivalent to, say, 1 pixel in an aerial photograph or a satellite image? It's not actually the same thing. Spatial resolution is quite a tricky subject. We're going to look into it in more detail soon, but it is perhaps the type of resolution that we want to define most clearly, and yet is the hardest to define. Spectral resolution is essentially what colors can we see, and how pure are those colors. So it could be red, green, blue, infrared, different types of infrared. But how pure is that color? We could also be talking about just visible light, a panchromatic image. So we can see the red, the green, the blue, but we don't know which is which. So we have a broad spectrum of light. For example, radiometric resolution. They were talking about the levels of intensity. Is it just a black and white image, or do we have black, grey, white, or black, dark grey, light grey, white, and so on and so forth, and we can build that up to many, many levels of intensity. Temporal resolution generally covers two terms, perhaps. How often do we measure, and how long does it take us to make a single measurement? So the temporal resolution, which I think we can see a similarity in the temporal resolution with the spectral resolution, in that we have where specifically we're measuring in time, and how broadly, how long does it take us to measure, to make that measurement. Is similar in respect to the spectral resolution, in that we can measure at a particular place on the spectrum, and how broadly do we measure it. Similar concept. We'll illustrate these a little better soon. So let's look at spatial resolution, the complex one, the one that really does require a little more attention. If we look at discrete data, hopefully you've seen this slide before. If you haven't, it doesn't matter, we'll go through it now. We have discrete data, something is there or it isn't, or it exists in a particular state. And in this example, we have some background, whether that's no data or whether that's some background class, and then some other object that it belongs to a different class that has a different state, distinct from this other. It exists there. That's the thing itself, say, and in the same case here and here. With this cell size, this larger cell size, we have to make a decision: does the thing exist here or not? This is not an easy question to answer, and the rules for making that decision will vary depending on what you're actually trying to do. But if we say 50% of the cell or a third of the cell has to be a particular thing or not, well, that's going to change our rules. But whatever the simple rule it is we're going to use, say 50% of the cell has to be one thing for it to be registered as being it. So because this is less than 50% red, it's grey, it disappears there. This is less than 50% red, or it's more than 50% grey, depending on how you want to define this, so it's grey up there. Equally, we can see this then just disappears. We don't measure this object. It's gone. It vanishes from our data. If we increase the cell size, decrease the cell size, increase our resolution, we can start to get the basic form of this object coming out, this red thing here. We start out, this is more than 50% of this cell is red, so this becomes red. Whereas here we can see that that's less than 50% is red, so it's grey. And again, we decrease the cell size, increase the resolution, and we get an even more nuanced image. So, or a better representation of this red object in the background. Good. So that's discrete data. When it comes to continuous data, which is more like the aerial photographs, satellite images, we can measure degrees of being a particular thing. So if this is, if our redness, if the grey now just represents absence, whereas the red is the signal we're trying to measure, the amount of red in a particular pixel or cell. So here we can see that we can give some sort of representation of how much red it is. And likewise here, so we get this continuous data. We get a slightly reddish pixel here, a more red pixel there, and a more red pixel there, and then the reddest pixel is there. Because there's mostly grey, a large component of this is grey. But then when we increase the resolution, decrease the cell size, we start to get a better picture of what's going on. And we can see here in this last one, we perhaps have an image that looks more like the true object. We've increased the resolution, we've reduced the cell size. Think about this whole continuous data, how many levels of redness there are in these images, how well that we then we can represent the form that is behind this data. Spatial resolution, radiometric resolution, spectral resolution, they all play in together. Spatial resolution is very difficult. So to examine that point farther, let's look at this aerial photograph here. We can see with our eyes in this image quite a lot of detail. The pixel size here in this aerial photograph is nominally 0.25 meters times 0.25 meters, 25 centimeters by 25 centimeters. And we can see, I think we can interpret with our eyes, we have these trees here, and we have grass, and we've got this gravel track going here, and we've got buildings over here. And what we have is railway lines going here and through here. You can see this is a double track, and this is a single track. And I think most of us can probably make out the railway lines here, each individual rail. That's interesting. We can see those. Pixel size, as I said, is 0.25 meters by 0.25 meters. And we zoom in there, and definitely, yep, we can see these rails. Okay, well, the rail is 0.15 meters wide. The width of any particular rail is 0.15 meters. So how are we seeing something that's smaller than the pixel size? Again, this is this problem with spatial resolution, but it's not that simple. What we have here is a long object. So we're inheriting information. In each pixel, we're inheriting information from the neighbors. There's this sort of information coming in from the sides, as it were, so that we can actually identify this long feature, even though all along its length it is smaller than 1 pixel. And so, given the Nyquist discussion earlier, we should say, oh, well, we shouldn't be able to see it. But of course, we have this extension in length, which means that we can. Also, we can see that it is easier to make out this rail where there's a higher contrast. So the brightness of the rail here, along here, which is kind of hard to see, perhaps it's not quite easy to see. Until we get to here, we have a very strong contrast in the background. The colors change dramatically, and then we can see it more distinctly here. So it's easier to make out this rail. So spatial resolution, radiometric resolution, which one is it there? Because we have this great change in the radiometric signal, or the radiometric resolution, or the strength of the signal variation coming through, we can more easily see the rail here. So that's how some of the other types of resolution play into our spatial resolution. So defining what spatial resolution, how small a thing we can see, is actually quite difficult. Again, the ground sampling distance may be 0.25 by 0.25, but we can see things that are nominally smaller than that. We also have to I'll bring into the discussion here something that perhaps we don't need to go into in too much detail on this course, but certainly in more advanced courses. I spoke about the information bleeding in from the side. We're inheriting data from along the sides here. This works in all directions. we have a phenomenon called mixed pixels, whereby the light isn't constrained to one particular pixel. It doesn't care which pixel it's in. The light in the physical world spreads out. And so we're getting light from this area actually being registered in these pixels, and light from this area being registered in these pixels. Not much. Most of the signal is coming from here, from where we would hope, but there will be some mixing of the signal coming in. That is a phenomenon called mixed pixels, and it's going to occur more along edges where we have these transitions from one type of signal to another. We're going to or at least notice it more. It's going to have a bigger influence on how we make the interpretation of what's there. That's so-called mixed pixels. It's a subject that we will deal with in more advanced courses. For now, let's just leave it at that. Spectral resolution. This is the idea of what colors can we see and how pure are those colors. So this is taken from the Sentinel-2 data sheet, where we have the spatial resolution here, 10 meters. This is how it's called. This is the name that they use. We quite often say spatial resolution. Is it the spatial resolution? No, it's the pixel size, really, what it equates to on the ground sampling distance, the nominal ground sampling distance. Band number, that just tells us this is so we know which band we're talking about, which data layer we are looking at. And so band number 2 in Sentinel-2 data is equivalent to this blue light here. So the blue light with a central frequency, or wavelength rather, sorry, of 496.6 nanometers. And we can see that on this, there are 2 satellites, and the other one, it's similar. It's not exactly the same central wavelength, but they're very similar. So these are where the central blue color is. What shade of blue are we looking at? And then we have this bandwidth, which tells us, well, how far from that as well are we gathering light in. The sensitivity to the light as we move away from the central bandwidth, in theory, decreases and will increase out to some edge. This is not. We'll just say that that's what happens, because that's a good enough image to deal with now. So that as we move off towards the edge of our bandwidth, it's less sensitive to the blue light. We're still calling it blue. It's not exactly the same shade of blue, but it's contributing to our blue signal. Same for the green here. We have this central green frequency, wavelength here. Sorry, I keep saying frequency when I mean wavelength. This is our green light with a certain amount of different shades of green coming in, contributing to this signal. Again, with the red and the near infrared. We have this for the different infrared frequencies here. So these are all beyond the visible light. These 3 are the visible light that we can see, and all of these are shades, as it were, of infrared light that we ourselves can't see, but the instruments can pick up. This actually is towards the violet end of the spectrum, and it's a large pixel size, but that doesn't matter. We don't use this. This is used more for calibrating our images. Don't worry about that. That's a remote sensing thing. So this is our spectral resolution summary. What colors do we have, and how pure are those colors? And this, so the bands, if we look at the different bands here, different colors. This is band 4, band 3, band 2. So we're registering the light as a grayscale image. We haven't assigned any color to it as yet. We're just registering the intensity of the light at that particular wavelength or frequency, and storing it as numerical data. And then we can combine this data into a color image. So if we take bands 4, 3, and 2, combine them, we get a so-called true color image. So bands 4, 3, and 2 from the Sentinel-2 data gives us the red, the green, and the blue light. And we can combine those to make this color image. This is approximately what we would see if we were up in space looking down. It's not exactly true color. Our eyes are slightly are sensitive to color in a slightly different way. Also, these don't capture all the variations that our eyes might see. So this is not exactly true color, but it's good enough. It's close enough, so that's what we say it is. And if we can then just use other bands as well, so we have, if we take band 8, band 4, and band 3, this particular combination is useful because we end up with band 8 is this near infrared. We can end up with a false color composite RGB image, which uses this standard representation for vegetation. So things that are red in this image are actually vegetation. The stronger the redness, the more vegetation we have, the healthier the vegetation. And this cyan color is associated with hard, dry surfaces, a lack of water, generally speaking. We have then to connect this, the spectral resolution. We're just going to quickly talk about spectral signatures and spectral signals. We'll come back to this in another lecture on remote sensing. But if we know that we're looking at a surface that reflects light, reflects and emits light in a particular way. So, for example, with vegetation, let's take this as a good example. We have this, the fact that vegetation is green, that we're familiar with, and reflects strongly in the near infrared. And then we see these dips, and it goes up and down here. So this is the signal, this is the light that we could potentially see if we could see all of the electromagnetic, or this portion of the electromagnetic spectrum. Soil, similarly, increases upwards to here into the near infrared. Well, that signal is what light is being given off by these particular surfaces. Here we have a representation of the bands that the Sentinel-2 can see, and if we match those up, so if we take our blue, green, and red, this is the sensitivity of, so to speak, the bandwidth is the blue light, the central band, and it measures all of this is calling blue, and we can measure that portion of the signature that's coming out. We can measure that in our satellite there. We'll capture that light coming in there. For the green, we'll capture that bit there or there. For the red there. For the near infrared, we can capture that or capture that. We don't see any of this here. That's all missed. We're not getting any of that signal. We're just getting that bit up there. And similarly, once we pull in the other bands as well, we can start nuancing, getting a little bit more detail in there, trying to capture these changes more accurately. But that gives us then our moving from the spectral signature to the spectral signal. So even though we have all of this information being sent out towards us and towards our sensors, due to the spectral resolution of our imaging tools, we're actually getting a spectral signal that only captures these little bits of information in these areas. So that's the spectral signature to spectral signal due to our spectral resolution.